Hello students and welcome back to Thermodynamics. In this part of the chapter, we are going to talk about pressure, volume, work. Now you may have this question in your mind कि क्या हम pressure और volume से work derive कर सकते हैं? Can we derive work from pressure and volume? Yes, we can. And the classic example for that is the steam engine, जिसमें हम स्टीम के प्रेशर और वॉल्यूम से वर्क डिराइव करते हैं जिससे इंजन आगे चलता है. सो प्रेशर एंड वॉल्यूम कैन बी कन्वर्टेड टू वर्क. What we will do to derive an expression for pressure volume work is that we will consider an ideal gas. This ideal gas is in a cylinder which is fitted with a piston. Now this piston is considered to be frictionless and weightless, which we know is not 100% accurate, but it's just to keep things simple right now. Okay, so we have a gas inside a cylinder and the cylinder is fitted with a piston. This gas, the ideal gas inside the cylinder, is at a pressure P1, it has a volume of V1 and it is at temperature T. And remember one thing students, when the gas expands, and eventually it will expand, its pressure and volume will change, but its temperature will be kept constant. So we are dealing with an isothermal process here where the temperature is kept constant. Okay, when this gas absorbs heat, okay, it absorbs heat, molecules will gain energy. जब molecules energy gain करेंगे, they will start moving fast. और जब वो फास्ट मूव करना शुरू करेंगे, वो पिस्टन को ऊपर पुश करेंगे. दे विल पुश द पिस्टन अप. ये सिनारियो कुछ ऐसा होगा where you can see that now the pressure of the gas is the same as the external pressure. तब तक पुश किया पिस्टन को जब तक internal pressure becomes equal to external pressure. External pressure कहेंगे या P2 कहेंगे, it's one and the same. So the system has absorbed heat and it has now reached a pressure of P2 or P external. The volume now is V2 and the piston has been displaced through a distance of D. यहाँ पर अगर मैं work का expression के बारे में बात करूं तो I can say that W is nothing but force into displacement. We know that work is force into displacement. यहाँ पर मैं force को माइनस एफ और डिस्प्लेसमेंट को डी लिख सकता हूं. इफ यू आर कंफ्यूज्ड कि यहां पर माइनस साइन कैसे आया, तो रिमेंबर वन थिंग, वी आर टॉकिंग अबाउट द अपोजिंग फोर्स एंड सिंस इट्स द अपोजिंग डायरेक्शन एंड फोर्स इज अ वेक्टर क्वांटिटी, सो वी कैन अप्लाई अ माइनस साइन हियर. नाउ वी नो दैट प्रेशर इज फोर्स बाय एरिया. So if I get area this side, I can write force as pressure into area. By substituting this in the earlier equation, I will get W is equal to minus P external into area into displacement. Now as a matter of fact, if we take any area and we displace it, it gives us a volume, right? Area into displacement is a volume, and if you look at the figure, you will see that when the piston is displaced, the resulting volume that we get is a difference between V2 and V1. So I can write this expression as W is equal to minus P external into V2 minus V1. That is the difference in volume, right? So this becomes my expression. W is equal to minus P external into delta V. So here we are, we have converted pressure and volume into work. W is equal to minus P external into delta V. All right. This is the expression for work done in irreversible isothermal expansion. It is isothermal because the temperature has not changed. It is irreversible because it has been done in one single step. If it was done in very, very small steps, infinite number of steps, it would have been reversible process, but this one was irreversible. So this is how we derive the expression for work done. Now what we can do is we can apply this formula that we have derived, that is W is equal to minus P external delta V, to different types of processes like a vacuum, cyclic process, isobaric or isochoric process. So we will apply this formula to all these different types of processes. It's a very important concept, students. Let's take a look at the first one, that is vacuum. Let's say we have the similar arrangement of a gas inside a cylinder capped with a piston, and this entire system has been kept in a vacuum. We know that in that case, the external pressure will be zero. There is no opposing pressure, there is no external pressure. In that case, I can say that P external is zero. And from the formula itself, you can see that if P external is zero, it will give you 0 into delta V, so work will also become 0. And this concept tells us that if you have a gas inside a vacuum, it will just expand without doing any work. This concept is also called as free expansion, and it tells us why astronauts have to wear spacesuit in outer space. Because if they don't do it, their bodies will start expanding, because the body will not do any work. It's a free expansion in the vacuum of outer space. Of course, the body will expand, but it will not explode. Our skin is a very tough fabric. It will resist all kinds of explosions, but the bodies will bloat, they will expand to twice the current volume, and that will not be a very comfortable or a very pretty picture. Okay, so in a vacuum, a gas just expands without doing any work. This is called as free expansion. If we consider the second process, that is a cyclic process. In a cyclic process, work done is something. It is not zero. It is something. For example, if I take out this pen travels a distance. It goes around, does all sorts of things, and it comes back to its original position. Will you say that no work has been done here? Of course not. Some work has been done. कुछ तो वर्क यहाँ पर हुआ है, बिकॉज ये पेन अपने जगह से मूव होके वापस उस जगह पे आया है. तो मैं ये नहीं कह सकता कि कुछ वर्क ही नहीं हुआ है. Some work has been done. So in a cyclic process, work done is not zero. Some work is done in the process. In isobaric process, our formula remains the same, because if you take a look at the formula, work done is minus P delta V. Volume is changing. You can see delta V in the formula. So volume is changing, but the pressure is not changing. So we have anyway considered this as an isobaric process where the pressure does not change. So the formula remains the same for isobaric process. Coming to the last one, that is isochoric process. In an isochoric process, there is no change in volume. Delta V is equal to 0. Now from the formula you can see that if delta V is 0, then the work done will also be 0. And this makes perfect sense. Earlier on, we had seen a beautiful frame of animation where we could see that when the piston was moving, it was cranking the wheel, it was moving the wheel. But now, as you can see, since this process is isochoric, there is no change in the volume. And if there is no change in the volume, the piston will not move. So the wheel will not be able to turn. So no work when the process is isochoric. I hope that is clear to you. So we have seen what is pressure volume work. We have derived the formula for isothermal irreversible expansion, and we have applied it to different types of processes. Let's now apply this concept graphically, and if we are able to understand that, then we will be able to apply that concept for maximum work. It makes perfect sense. Since pressure and volume are giving me work, I want to know how can I get maximum work. All right, let's take a look at the formula that we know, that is W is equal to minus P external delta V. We've just derived that. this derivation is for isothermal irreversible expansion, because the temperature is constant here and this expansion was done in a single step. Now if I plot a graph for this expansion, initially the gas was at the state A, where the pressure was very high and the volume was pretty low. So you can see point A is that position. From here, the gas expanded to point B, where you can see that the pressure has now decreased and the volume has now increased. So this is now the position of the gas, the state of the gas. This red line indicates the process of expansion. Here, if you want to find out what is the work that has been done, all you need to do is multiply the pressure with delta V. What is P external? Just think about it. P external is nothing but the final pressure, also called as P2. So from 0 to P2 will be the external pressure. What will be delta V here? Delta V will be nothing but the difference. V2 minus V1 will give me delta V. So if I take this rectangle, the shaded area, the blue area, this represents the work done. That is pressure into difference in volume. Now, we know how to apply this concept graphically. We know how to find out the work done graphically for irreversible process. Let's say this same expansion from point A to B, instead of a single step, it was done in multiple steps. Okay? So in the first step, you will see that this shaded region will be the work done. In the second step, again, we will have some work done. And the same will apply for the third step, okay, and the fourth step. So it is clear that when the same process, the same expansion, instead of doing irreversibly, instead of doing it in one step, if we do it in multiple steps, we can see that the shaded region is more. So more work is achieved. So now imagine what will happen if I do the same process reversibly. Instead of irreversibly, that is one step, I now do it reversibly, that is infinite number of steps. So you can see the same expansion now being done in infinite number of steps. In every single step, I will be able to derive some work, and effectively the work which I get will be maximum, right? I think that's very evident from the graph right here. So if the same expansion is done reversibly and the same expansion is done irreversibly, you will see that the reversible process has got maximum work. Okay, so I hope that is clear. What we have done so far is that we have seen that pressure and volume can give us work. We have also seen the expression for this work, the derivation of this expression right here. We have applied this expression to different types of processes, and we have seen the graphical representation. Okay, we have also seen that reversible process will give you maximum work as compared to irreversible process. Let's now derive an expression for maximum work for isothermal and reversible process. याद रखिएगा स्टूडेंट्स, जहां पर भी ये दो टर्म्स अगर साथ में आ गए, दैट इज आइसोथर्मल एंड रिवर्सिबल, वहां पर हमारा वर्क डन मैक्सिमम होगा. रिवर्सिबल का तो मैंने अभी आपको दिखाया था, ग्राफ में हमने देखा था कि इन द रिवर्सिबल प्रोसेस वी आर हैविंग मैक्सिमम नंबर ऑफ स्टेप्स एंड वी आर गेटिंग मैक्सिमम वर्क. आइसोथर्मल में क्या मैक्सिमम वर्क आता है? जी बिल्कुल आता है, एंड वी विल सी दिस in the first law of thermodynamics. Right now, just take it from me that isothermal process also gives us maximum work. Right? We will study that in detail in the first law of thermodynamics. Now, in order to derive this expression for maximum work in isothermal and reversible process, we will again consider a gas with n number of moles. Again, this ideal gas, n number of moles, it has been kept inside a cylinder, and a piston which is weightless and frictionless has been kept upon it. So you can see the setup right here. Okay, now in this particular system I can say that the initial volume is V1 and the initial pressure is P. Let's just keep it as P right now. What we need to understand is that the external pressure is slightly smaller than the internal pressure of the gas, and it makes perfect sense. In every single step, we will have a small expansion, little expansion, as you can see right here. Okay, in every single step, there is a little amount of expansion. The overall change in volume is delta V, but the small change in volume for every single step is dV. Now, obviously, if there is going to be a small change, a small step, it means that the difference between the driving force and the opposing force, once again, the difference between the driving force, that is the internal pressure, and the opposing force, that is the external pressure, the difference between these two forces is very less, and that's why the steps are very, very small. I hope that is clear to you. Okay, so that's why we can say that the external pressure is just slightly smaller than the internal pressure, because the steps are also very, very small. So in each step, the external pressure is slightly less than the internal pressure. Now here we can say that the final volume after expansion is going to be V2, okay, and the final pressure is eventually going to be P external, that is the external pressure. Two things are really very important here. First is the formula that we all know, that is W is equal to minus P external delta V. And the second thing that is important here is that the external pressure is slightly smaller than the internal pressure. So we can say that P external is P, that is internal pressure, the initial internal pressure, minus dP, the difference in the pressures. Okay, now let's start with the derivation. Right here we have a teacher next to us, but this is still my class. All right, so we know that work done is minus P external into delta V. We have the expression that we have just now derived, dW is equal to minus of internal pressure into small change in volume. For every such small change in volume, small amount of work will be done. So in order to get the overall sum, in order to get the overall collection, right, we will integrate the expression. So the total work done in the entire expansion from V1 to V2 will be this. The integral of small amount of work done between the 2 points is equal to the integral of minus P dV between volume V1 and V2. For those of you who are not very strong with integration, just remember that integration is a sum. It's like a summation. It's like addition of small points. And here we have lots of small changes in volume. We have small work being done in every single step. So we are going to add that up together, and that is the meaning of integration. Now we know that the overall integration of the work is going to give us W max, maximum work. Okay, and as far as the right side is concerned, we will take out the negative sign because it is a constant, it cannot be integrated, and we will keep minus P dV inside the integration. But now there is a little problem here. Let me tell you what it is. Inside the integral sign, we have dV, and that's why the expression of pressure has to be brought in terms of V. For example, we always have integration of x square dx. If we have a dx, we need an expression in terms of x itself to integrate it. Similarly, here we have the integration expression in terms of dV. So how can we integrate in terms of pressure? We will have to convert this P in terms of volume and we can do that with the help of ideal gas equation, that is PV is equal to nRT. I can write pressure as nRT by V. So there we have it. We have pressure in terms of volume. Let's take this nRT by V and substitute this in the earlier expression. So we will get W max is equal to, minus is still outside, integration between V1 and V2, nRT by V into dV. So here we know that there are some other things which are constant, just like when माइनस साइन वॉज कांस्टेंट, जब माइनस साइन कांस्टेंट था उसको हमने इंटीग्रेशन साइन के बाहर निकाल दिया था. यहां पर भी कुछ चीजें हैं जो कांस्टेंट है. नंबर ऑफ मोल्स आर कांस्टेंट, दैट इज n, बिकॉज वही सेम गैस है जो एक्सपैंड हो रही है. ना तो कोई मोल्स ऐड किए हैं ना कोई मोल्स बाहर निकाले हैं. इट इज द सेम नंबर ऑफ मोल्स ऑफ द गैस which is being expanded. R is also a constant because it's a universal gas constant, and T is also constant because, well, see the heading, it's isothermal process. Temperature is going to be constant. So we can say that W max is equal to minus nRT into integral of 1 by V dV between the limits V1 and V2. Now this is where the formula for integration comes into play. We know that integration of 1 by x dx is natural log of x. So that's exactly what we are going to do here. When we apply the integration, we will get natural log of v between the limits v1 and v2. Let's now apply the limits. When we do that, we will get the upper limit minus the lower limit. That will give us the integration. So let's do that. We have W max is equal to minus nRT into natural log of v2 minus natural log of v1 by application of upper limit minus lower limit. But we know that log of a minus log of b is log a by b. So again, we can write this expression like this. We can write it as W max is equal to minus nRT into natural log of v2 by v1. What we can do here is we can take this natural log and we can remove 2.303 from it. If we do that, the natural log will get converted to log base 10. अगर आपको ये नहीं पता है कि इसको हमने log base 10 में क्यों कन्वर्ट किया, तो मैं आपको बता दूं, log base 10 यानी कि हमारे लॉग बुक्स के वैल्यू. ओके, नेचुरल लॉग हम अपने लॉग बुक में नहीं देख सकते, तो जब हम कैलकुलेट करते हैं न्यूमेरिकल्स में, वी रिक्वायर लॉग बेस 10 जो वैल्यूज हमको लॉग बुक्स में दिए हैं. सो इट इज इंपॉर्टेंट टू कन्वर्ट नेचुरल लॉग इनटू लॉग बेस 10. हाउ डू वी डू इट? बाय रिमूविंग 2.303 outside, not minus 2.303, it is 2.303. you can see that minus sign तो पहले से ही था, राइट? हमने सिर्फ 2.303 को यहां से बाहर निकाला है. अच्छा, now we know from 11th standard concept of Boyle's law that P1V1 is equal to P2V2 when temperature is kept constant for a given volume of gas. By using that formula, P1V1 is equal to P2V2, we can cross multiply and we can get V2 by V1 is equal to P1 by P2. So we can also substitute that in our earlier expression and get this value. W max is equal to minus 2.303 nRT into log base 10 P1 by P2. So there we have it. You can see both the formulae on your screen. Both these formulae are very, very important. One is in terms of volume and the other is in terms of pressure. W max is equal to minus 2.303 nRT into log base 10 of either V2 by V1 or P1 by P2. ओके, रिमेंबर स्टूडेंट्स, ये फॉर्मूला हम तभी यूज करेंगे जब हमको क्वेश्चन में क्लियरली मेंशन्ड होगा आइसोथर्मल एंड रिवर्सिबल कंडीशन. सिर्फ वहां पर ये फॉर्मूला अप्लाई किया जा सकता है. नाउ लेट्स जस्ट क्विकली टेक अ लुक एट द डिफरेंट साइन कन्वेंशंस, बिकॉज ये एक चीज है जो यहां पर थोड़ी इंपॉर्टेंट है. याद रखना स्टूडेंट्स, वर्क का साइन कन्वेंशन जो है वो बहुत ही सिंपल है. व्हेनेवर वी हैव कंप्रेशन, ओके, कोई सिस्टम कंप्रेशन अंडरगो कर रहा है, कंप्रेशन अंडरगो करने का मतलब है work is done on the system. That means it is getting compressed. Okay, so compression means work is done on the system. In such a case, you will take the work as positive. And for expansion, work is being done by the system, and here you will take the work sign as negative. Okay, remember these sign conventions, these are very, very important. The second sign convention which I want to tell you about is of energy, heat, enthalpy. These are all different forms of energy. ठीक है, तो इसका साइन कन्वेंशन बहुत ही सिंपल है. वी हैव endothermic reactions where heat is absorbed, energy is absorbed. In such cases, energy is taken as positive. And for exothermic reactions where energy is released, sign is taken as negative. इसका एक एग्जांपल आप याद रख सकते हो. जब जेब में पैसे आते हैं तो बैलेंस पॉजिटिव में जाता है. सिमिलरली जब एनर्जी अब्सॉर्ब होती है, एनर्जी सिस्टम में आती है तो पॉजिटिव है. जब जेब से पैसे जाते हैं तो बैलेंस नेगेटिव हो जाता है. एंड सिमिलरली जैसे ही एनर्जी बाहर जाती है एक्सोथर्मिक प्रोसेस में, एनर्जी का साइन कन्वेंशन नेगेटिव हो जाता है. याद रखना स्टूडेंट्स, वी हैव सीन दैट प्रेशर एंड वॉल्यूम कैन डिराइव वर्क. वी हैव ऑल्सो सीन कि कैसे प्रेशर वॉल्यूम वर्क को हम डिराइव कर सकते हैं आइसोथर्मल प्रोसेस के लिए, विच इज इरिवर्सिबल. W इज इक्वल टू माइनस पी एक्सटर्नल डेल्टा V. उसी को फिर हमने अप्लाई किया 4 अलग अलग तरह के प्रोसेसेस में. उसको फिर हमने ग्राफिकली स्टडी किया और फिर हमने मैक्सिमम वर्क का एक्सप्रेशन डिराइव किया. एंड जस्ट नाउ हमने वर्क और एनर्जी के साइन कन्वेंशंस देखे जो कि बहुत ज्यादा इंपॉर्टेंट है. विद दिस आई कैन शो यू all the formulae for the first type of numericals which are asked in thermodynamics. The first one, as we know, W is equal to minus P external delta V. The second one is W max is equal to minus 2.303 nRT into log of V2 by V1, and that log is to the base 10. And the third formula is the same as the second one. It's just that instead of V2 by V1, we now have P1 by P2. याद रखना स्टूडेंट्स, सेकंड एंड थर्ड फॉर्मूला हम वहीं पर यूज करेंगे जहां पर आइसोथर्मल एंड रिवर्सिबल कंडीशन स्पेसिफाई किया होगा. एक चीज आपको पता होनी चाहिए यहां पे, दैट द वर्क डन is minus P external delta V in the first formula. Pressure will be given to us in atmosphere and volume will be given to us in liter. Atmosphere into liter is not joule. Atmosphere into liter is liter atmosphere. अब ये लीटर एटमॉस्फेयर को अगर मैंने 101.3 से मल्टीप्लाई किया तब जाके मुझे जूल्स मिलेगा. तो इस बात का जरा ध्यान रखना स्टूडेंट्स. इन द एग्जाम वी विल बी गिवन द प्रेशर इन एटमॉस्फेयर एंड वॉल्यूम इन लीटर्स इन मोस्ट ऑफ द केसेस, लेकिन जो वर्क डन होगा वो हमसे जूल्स में पूछा जाएगा. तो जब आप इनको मल्टीप्लाई करोगे आपको आंसर आएगा लीटर एटमॉस्फेयर में. उसको फिर आपको मल्टीप्लाई करना होगा 101.3 से, so that you can get your answer in joules. So let me just keep that aside, okay, so that it becomes convenient for you to see it. Remember students, 2 and 3 तभी यूज होगा जब isothermal and reversible process होगा. Thank you so much for watching. I'll see you in the next module where we will discuss the concept of internal energy and finally the first law of thermodynamics. Thank you so much for watching. If you like our lectures, do like, share and subscribe. Thank you.